This is the second lesson on the refraction of light. And I first will be using the textbook's example. Now in here, if you turn your books to page 48, you will see there's two buckets there. The first bucket doesn't have any water. The moment you pour the water in, the cone appears. And it's not magic, I can tell you that. It's related to the refraction of light. So let's take a look at what's happening here. Now, in here, when the cone is at the bottom of the bucket, our eyes cannot see it because it's blocked, as you can tell here, it's blocked by the side of the bucket. You cannot see through the bucket, so that's why you cannot see it. Now, the moment you put the water in, the water will have the same property as a medium. So the light will be traveling from the cone all the way across the boundary. So in here, this cone here, the light of it the size of it will be traveling this way up this side with the solid lines on it. And then when it passes through the boundary from water to air, it will want to be bending away from it, from the normal, because it starts from the slow side and it bends away from it. And the moment it bends away from it, it enters your eye. So it appears to be the cone you are seeing actually appears. The reason for that is, if you extend that straight line with the dotted line over there, you will see the cone appear to be in a new position. And we have a name for that. We call that an imaginary image. Okay? So it's not real, it's virtual. Now, so in here, the object started from the bottom of the bucket. It moved up. Actually, the physical position of it hasn't moved, but the cone appears to be falling on it. And that is, then we got a name for that, and we call that apparent depth. So in here, if you go to the beach or swimming pool next time, look at the bottom of the pool and you will see that the person appears to be having a shorter legs. That's the reason why, because the light actually bends away when it enters air and it generates an apparent depth. Now, in here, the next example. For example, in here we've got a bird, the kingfisher. When it's looking at a fish, it cannot actually just attack that image, because if he just keep on hitting that image, he's not going to catch anything. The fish is actually in a lower position, it's more depth. So in here, if you take a look at it, you see that the appear image with the dotted line here, comparing to the actual image, is actually lower this way. And in here you will see there are different index for the seawater and the lake. So it just tells you that how much it bends away more in each diagram, that's all. And you can try that with a ruler or chopstick. If you put it into the water, you will be able to see that it appears to be broken and it's bent away from it. And in here, that's the chopstick, and you will see that the light actually bends away from it, and that's why you will see the virtual image of that. Okay, so now let's go back to the notes. So in here, So in here, the light from the object undergoes refraction in here when it leaves the water-air boundary. And the object itself, the cone in our first example, would appear to be shallower than the real position. So if you reach the cone in the water, you will not be able to watch it, actually touch that, because that is not a real position of that cone. It's actually an image. And we have a name for that. We call that apparent depth. Okay? A-P-P-A-R-E-N-T, apparent depth. And the same thing happens in the swimming pool. You will see that it appears to be shallower than the actual depth is. Okay? And now in here, let's put in the drawing. Now, in here, how do we draw it? In the first example here, we have the cone and it appears to be rising. How will we be able to draw that? We will be able to do that by, first of all, drawing in the normal first. So in here, we put down normal, the normal line first, and it's just a convention. People actually use dotted line in the middle as the normal line. That's the first step. And then the second step, you pick a point from the cone, for example. Let me use different color. It's going straight up to the water-air interface, and then it will bend away from the normal because it's entering from a slower medium of water and enter into a faster medium of air. So you compare these two angles, it's bending away from the normal. So that would be the second step. So after that, what do? Then you use a dotted line. So in here, from your eyes, that line, from the solid line, it turns into a dotted line. And then you draw in the imaginary image of that cone. That's how you draw the apparent depth in this kind of drawing. And now, in the second example, this one I need to expand a little bit more because it's really hard to draw in this. Now in here, the first step is as normal, put in the normal again. So we put in normal, and after that we do the solid line. So from the bottom of the chopstick going up, and when it hits that interface, that water air interface, it will bend away from it. So in here, this angle between the normal, you can barely see it, but it's still there. It's larger when it exits the water air interface. It bends away from the normal. It's same as what we have done in the previous example. That's the second step. And the first step is to extend it. So in here, from your eye, that solid line coming out with the dotted line this way. Okay? So you will be able to see that it's extended out this way. And then you will be able to draw the remaining chopstick with the dotted line to finish this drawing. Now, in the next example, and if we place a glass on a textbook, the words on the textbook appears to be falling on top because of the apparent depth. So in here, what we need to do is we pick a point here, and then from that we will be drawing upward with the straight line. Once it enters the glass air interface, same as before, it bends away from the normal. So in here, we're comparing this angle here to this angle here. It's larger, it's bending away from normal, okay? So in here, that's what we need to do. And do the same thing on the other side, so you'll be able to have the solid lines done first. After that, you will need to put in the dotted line. So from the solid line, you need to extend it, this dotted line, on both sides, and it meets at the center. And that point is in reference to where the textbook's letters appear to be. So it's moved all the way to a shallower position with the apparent depth. And from that, let's finish the remaining questions. So in here, when the person is looking at the other person's leg, it appears to be closer. But if you flip it the other way around, when you are swimming in the water, let's say you are scuba diving and you're looking up into the sky actually appears to be further away. And it's explained by the lines drawn on the diagram. And in here, when you look at something which is in water, the object appears to be closer. And when you're in water looking at something, the object appears to be further away. So that's the reason why when you're looking in the goldfish always seem to be looking at you and looking strangely. The reason for that is when the fish is looking at you, it actually is looking further away, it appears to be. So it's just so that the goldfish think that, oh, it's so far away. Now, this is only the first topic on the apparent depth, but in the second part, we have the EM wave, EM spectrum. The reason for that is because we are talking about light. Light is actually a form of wave, electromagnetic wave. And in here, there are a lot of examples that I could show you. And some of the videos are actually pretty easy to understand, while others is pretty difficult to comprehend what they're talking about. So let's show you the light video first on the crash course. So in here, some of the video here is actually quite useful on the astronomy. Let's see. Yes, the first one.
Hey, Phil Plait here, and this is Crash Course Astronomy. In last week's episode, I mentioned that nearly all the information we have about the universe comes in the form of light. But how does that light get made? What can it tell us about these astronomical objects? And honestly, what is light? Here's a hint.
Okay, go back in a second here. So you see this person, what is he doing? Let's see, we can do 15 seconds. No, it doesn't work. So in here,
here's a hint.
you see what he's doing with his hand? He's waving, because light is a light wave. It's important to know that, because from that he carried on to talk about a lot of different things, and I'm not going to show you a whole video, but I want to show you around a minute and give you a sense of what he talks about.
Radiation. The details of this are very complex. but we can make some pretty good overall observations about light just from thinking of it as a wave. If you're floating in the ocean, you'll move up as a wave passes you, then back down, then back up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a wave, it has a wavelength.
So in here, that is important to look at this
Up again when the next wave rolls by. The distance between these crests in the wave is called the wavelength. Since light is a
So in here, that's why in here, in the last video, we talk about lambda. Lambda actually is representation of how far away is this distance, is the wavelength from the top to another, the top part to the other side of the top part. So in here, that is some of the ideas. If you want to carry on watching this video, I encourage you to do that. Please do that because actually it gives you a good idea of what light is. Unfortunately, we have to go back to notes and to carry on with some of the explanation. So in here, that's why you see the word here, the wavelength. That's one of the ideas. From one side to another. So in here, the longer the wavelength, the further it will travel. For human beings, we only have a pretty short wavelength of, you see here, the visible light. It's only a short wavelength we can see. But outside of it, we got all kinds of different things. We got infrared, microwave. On the other side, you got the UV, ABC, and then you got the X-ray and the gamma ray. The last one here is called gamma ray, and those are the cosmic waves. Those you would get a lot if you go into the space, and that's why you need a spacesuit to make sure those things doesn't get to you, and those things will cause cancer. Now, those waves enters the cell and will destroy the cell wall, and it will mutate your DNA as well. So that's why you want to have a spacesuit when you are going up into the outer space. And there are more than enough videos online, you can check it out later on, but we still have to carry on with our lesson, so let's move on here. Now, so in here, you see the EM wave is the electromagnetic wave here, and it will have all different kinds of properties. Some of the properties we have talked about from our previous lessons. We have the refractions, and currently we talk about this one, the refraction. The other ones, we will talk about it later, and maybe some of you will take the Form 4 or Form 5 course on this, and you will learn about that. And in here, you will see that all these are related with in a equation. You see the V is the velocity, basically for you now is speed, and it's equal to frequency times the lambda, the one we talk about, the one we talk about up here, you see? So, oh, by the way, the longer the lambda is, the short the frequency will be smaller. So they have an opposite proportion. They are reversely proportionate. Now, so from here, here's some of the ideas and some of the units you will normally see if you talk about the frequency F here, the lambda length, and the time, in the time scale. So in here, some of the normal ones you will see is Hertz, Hz, and then the lambda is measured in terms, sometimes you will see that millimeter, and this is the micrometer, and this is the nanometer. So you see it's decreased by the factor of 1,000. In here, 10 to the -3, 10 to the -6, and 10 to the -9. Okay? And the same thing can apply to seconds. It's microsecond and the nanoseconds. See? It's just exactly the same thing. Now, so in here, basically what this page is talking about is using the equation here. This one, V equal to F times lambda. And with this equation, you will be able to change the subject to find the frequency. For example, frequency is equal to the V over lambda. And in here, as in this example shows you, we got the speed of light. And let's see, traveling the thing. Yep, we got the speed of light of 3 times 10 to the power 8, and that is the velocity, and it's divided by the lambda. And in here, we got the limit of 4 times 10 to the negative 7 and 7 times 10 to the negative 7. So those two are the extreme cases. One is the lowest frequency and the other one is the maximum frequency it could get. Okay, so that's why we're trying to limit those with the wavelength length. And from that, we can calculate the answer. And just from that, we will be able to get these two frequency in terms of hertz. Okay, so that is how we generate this frequency range of visible light. We just do it by calculation. Now, in example 2, is pretty straightforward. Actually, we use the same thing again, but this time we are talking about the units of 25 nanosecond. And in here, nano means, again, referring to the table on top, is 10 to the negative 9. Okay, so you need to know that. And the speed of light, you know that is 3 times 10 to the power 8, as we have used in the last example, example 1. Now, in here, we'll find the object. And we want to find out that why does this divide by 2? It's because it's emitting it and receiving as a pulse. And in here, it's just an additional exercise for you trying to do this equation. Besides that, we are not going to put that in the exam. Anyway, there's one more table we have to go through first. And let's see, we have enough time at the end to do one more topic on this today. Now in here, some of the informations that could be useful. For example, the EM wave. We got the microwave, you got infrared, you got the microwave, infrared, and the visible light, the one you can see, and the UV. Okay, so all these have applications on how to we use that. Okay, so how do we, for example, how do we receive the radio wave? With the radio signal, we need to have radio itself to receive it. And the microwave receiver, for example, and those would have an application of using in the satellite, for example, or radar. And for the infrared, as we have in the school, you have the infrared sensor, so you can sense your temperature. And the visible light is quite useful in terms of the solar cells. And in order to improve the efficiency of the solar cell, it's actually better if we can capture more of this, not only between the visible light, but a lot bigger or the wider range of this light. So it would be able to increase the efficiency. The light we cannot see, the infrared or UV, if we can turn it into energy as well and absorbed by these solar cells, the efficiency of the solar cells would improve so much more. But it's still a work in progress. And of course, you know that UV would be able to sterilize it, to kill off all the bacteria you don't want. And the X-ray is for medical use. And the gamma ray, actually we use that in the radiation form to help people to kill off the cancer. Okay, so that's all I want to talk about the EM wave for now, because it's one of the topics that we only have half a lesson to talk about, so we don't have that much time to talk about it. But after that, we have one more thing to talk about. It's called the total internal reflection. Now, the first part of it, the one over here, this part, actually is not in your exam because it will require you to know the Snell's law, but we are not going to do that. Okay, so the first part, for your own reference, you can try it, enter those numbers, and you will get a math error from your calculator. So something is going on, something doesn't make sense. So that's what we're trying to do with the lower part, to explain to you what does it mean by the total internal reflection. Something is happening to the light. So let's take a look. Now in here, so let's take a look at the conditions for the total internal reflections. Now, when a light beam travels from an optical denser medium to an optical less dense material, that means it wants to bend away from the normal. Okay, so we have covered that in our 2 lessons already. You should remember that by now. If the angle of incidence increases, the angle reflection also increases. So basically, one increase, the other one increase as well. So now imagine what happened if the refracted angle became 90 degrees, as in this case, becomes 90 degrees. What will happen? And yes, I know that your notes do not have this drawing, and please draw in the small diagram over there to demonstrate to you what is happening. The light is actually traveling at the edge of that interface of the glass air, for example. It's going away, but where does it go? That's what we're trying to explore here. Okay, so in here, let's take a look at the diagrams. So in the first case, we got glass on top. The incident angle is 20 degrees. It's bending away. It generates a 30-degree angle here. Okay, so it makes sense. And you don't need to draw in this part. It just tells you the weak refracted wave. You don't need to know this part. It's refracted. You don't need to know this part yet. And in here, if you carry on to increase from 20, it increased to 35. So this angle here, you see that is getting bigger and bigger. So when you increase this angle to 41.8 degrees, what we talk about on top will happen. It will turn into 90 degrees going straight across. But after that, if you carry on to increase it to, let's say, 43 degrees and so on, it will just have a normal reflection, as what we talked about it in the last 2 lectures already. Okay, so in here, that's the case we don't consider. We only look at the one in the middle. So we only look at this case. At 41.8 degrees, it will enter into, all the lights would go 90 degrees. Where does it go? Okay? So let's put into words of what we have observed so far. So in here, when you are looking at how the lights travel from an optically denser medium to a less dense medium, okay, please make sure you're entering from a denser to less dense medium. Okay, the other way around, it does not work, because the light itself, think about it, what will happen to the light wave? it will bend towards normal. It will not bend away from normal. So only for this to happen is for it to be traveling from the denser medium to a less dense medium. So if the angle of incidence becomes large enough, larger than the critical angle, in the next page we will talk about what is the critical angle, there is no refracted wave. There's no refracted wave at all. Instead, the light wave will undergo refractions only, and it's called the total internal refraction. That's what we will get from this total internal refraction. And in the next lesson, we probably will have time to talk about diamond. Apparently the girls like that. And well, for me, it's just a walk. I don't know why it's so expensive. It's hard, but many things can be really hard as well. But anyway, so that's what we will look at it, because that's what we want to achieve. If the light enters into a diamond and it traps inside the diamond, it will make it look really sparkling and nice, apparently. And that's why people pay a lot of money for that. I can tell you that they're not paying it for the hardness, not the property. So in here, let's take a look at some of the drawings here. Let's finish it off. Now, in here, next question is, will total internal refraction occur if the wave travels from the optically less dense to optically denser medium? As we have already covered that with the answer already, from less to denser, will it happen? The answer is no. There's no way it will happen. The reason for that is when you can take a look at it from the air. If it's actually starting from a really tiny angle here, it will want to bend even shorter. And when you bend it away increasingly all the way next to almost 90 degrees, the maximum you can get is only 42 degrees. It's not even half of what it could achieve. So there is no way it could bend away from it. It's always bending towards the normal. It wants to bend to the normal. Okay, so that is the reason why it cannot be achieved this way. Okay, so please make sure you understand that we are always starting from the So in here, we are always starting from the denser material to the less dense material. Okay, so that is the property you have to remember. And in the next part, we have the critical angles. And in your notes, we will not have too much time to cover that. And as I realize the time, we only have around 5 minutes in this video to cover it. So I will only say that we will be talking about this in a bit more details in the next video. And in here, for the critical angles, we are looking at how the light will be traveling, entering this way. That's what we are trying to examine. What is happening to the light wave when it goes into something else, and then as long as it's not air, because in here this line actually is important, must not be air. It cannot enter into air, because there is nothing you can do about that, because air is the fastest you can get in with the light. So that's why in a case, of course you can argue that you can use vacuum, but it's really hard to achieve in the high school level to examine that. So right now we stick with this. The light wave cannot be traveling into the air, exiting some other medium into air. We cannot do it, and we could not achieve that in this level. Okay? Okay, so now I will stop the video here, and we carry on with from this point in the next lesson.